So today we are going to be learning about nuclear chemistry. First of all, there are three types of nuclear radiation. The first is alpha radiation. This is actually a particle. The symbol for alpha particles is the Greek letter alpha, which looks kind of like a fish. If you cover up the top part of the fish, you can kind of see how this eventually became our lowercase a. The next type of radiation is beta radiation. Here's the Greek letter beta. You can see how this became our letter B. And gamma radiation is the third type, and well, that didn't exactly become our letter C. Oh well. So alpha and beta radiation are particles. Gamma radiation is not a particle, it's a high energy ray. So we have particles and rays. First of all, an alpha particle is made of a helium nucleus. Inside a helium nucleus, there are 2 protons and 2 neutrons. So the formula is helium, a mass number of 4 for 2 protons and 2 neutrons, and an atomic number of 2 for the 2 protons. And the charge, you have 2 positive protons, and the neutrons are neutral, so overall that gives you a positive 2 charge. The mass is 4 because the 2 protons and 2 neutrons weigh 1 atomic mass unit each. What will shield you from alpha radiation is a piece of paper, your outer layer of dead skin cells, or even your clothing. So it's very easy to stop alpha particles. In fact, they're not too dangerous because of that unless you would eat something that's producing alpha particles. And then that, your inside, your organs don't have skin around them. And so that's why it would be very dangerous if you ate something that produced alpha particles. Next is beta radiation, and it is made of fast-moving electrons. Now, E stands for electron. The mass of an electron is approximately 0. The atomic number is the number of protons. Wait a minute, these are electrons. Well, the proton is the opposite of an electron. Electron's opposite of a proton, so a -1 for the atomic number. And the charge, of course, of electrons is -1. They weigh almost 0. And beta particles are a little harder to stop. You have to have a thin piece of wood or a sheet of aluminum foil. So if you've ever seen where some people would wear aluminum foil inside their hats, one thing they might be trying to protect from is to protect from beta radiation. And gamma rays, there's the symbol. There's no formula because, it's the same as the symbol, because it's not a particle. It's a ray of light. It's a type of high energy light. And so that's what it's composed of. That's what gamma rays are made of. A ray of light has no charge and weighs nothing. And it's really hard to stop gamma radiation. That's the most dangerous type. It either takes several inches of lead or 10 feet of concrete to stop gamma radiation. So it's actually really hard to stop. This is why people will build, say, an underground bunker lined with lead and concrete. This is to stop gamma radiation, which is the most dangerous type. So the first thing we need to be able to do is to predict the products when something decays by alpha decay. A radioisotope is an isotope of an atom that is radioactive. So uranium-238 is a radioisotope of uranium. It's a radioactive isotope. We look up on the periodic table, uranium is atomic number 92. So that's where I got my 92 from. Now they tell you that it decays by alpha decay, so it makes an alpha particle. So write 4/2 helium, plus it'll make something else. Now, 4 plus what adds up to 238? Oh, 4 plus 234. 2 plus what adds up to 92? Oh, 2 plus 90. Now let's figure out what element this is. Atomic number 90, we look that up on the periodic table, and it is the element thorium. So, capital T, lowercase h. And now we have just predicted what will happen. So uranium, when it breaks down through alpha decay, will actually turn into a new element. It will make thorium, and it will give off an alpha particle of radiation. So this is why a nuclear reaction gives off so much energy. It actually rips apart the atom, makes a brand new atom, gives off some radiation, and it also even gives off energy. It actually destroys the tiniest bit of matter in the atom and converts it to energy. A tiny bit of matter makes a ton of energy, and that's why nuclear radiation gives off so much energy and is so good to use in nuclear power plants. So now, remember the law of conservation of mass. Mass or matter can neither be created nor destroyed. So wait a minute, I thought I just said that it would destroy the matter, but it can change forms. So it converts from matter to energy. And in fact, this is what Einstein's famous equation, E equals mc squared, means. It means the mass of the atom that you destroy times the speed of light squared will equal the amount of energy that's given off. Now, so the mass that's destroyed is this tiny little number, but the speed of light is really fast, and if you square it, it's this huge number, okay? So a little bit of mass times this really big number gives you a ton of energy. That's why it's good to use in nuclear power plants. Now, alpha decay reduces the mass of an atom by, well, remember mass number over atomic number. The mass of 238 went down to 234. It went down by 4, just like the formula said. And the atomic number went from 92 down to 90. It went down by 2. That's what alpha decay does. It takes the mass of the atom and reduces it by 4, the atomic number of the atom, and reduces it by 2 and makes a new element. By the way, only nuclear reactions can make brand new elements. Matter can neither be created nor destroyed. You cannot make a new atom. You take the atoms you have and rearrange them. But in a nuclear reaction, a tiny bit of mass is actually transformed into energy. And so that's why nuclear reactions give off a ton of energy. Chemical reactions can give off some energy. All right, now the product of that reaction decays by beta and gamma decay. So we're going to take thorium-234 and 90, and it produces beta and gamma radiation. So beta is 0 over negative 1e. No, this is not a dash IE. It's a 0 over negative 1e. And it makes some gamma radiation. And what else will it make? You ignore the gamma radiation. It's a ray. It's not a particle, so you don't have to worry about anything. 0 plus what will give you 234? 0 plus 234. Now be careful. This is a negative 1. What minus 1 will give you 90? 91. 91 minus 1 gives you 90. See, it's kind of weird, isn't it? The 90 went up to a 91. Now, the next thing we need to do is figure out what element this is. We look up the 91 on our periodic table, and that is protactinium. So, capital P, lowercase a, and we're done. Beta decay increases the atomic number, which is the bottom number, right? 90 went up to 91. So it increases the atomic number by 1. And it keeps the mass number, 234, 234, it keeps it the same. All right, next we're going to learn about half-lives. When nuclear decay occurs, it always has a half-life. The half-life, or T1/2, is the amount of time required for half of a radioisotope to decay. So half-life is kind of weird. Let's say that you have a half-life of 15 seconds, okay? Every 15 seconds, half of your sample will go away. So let's say you have 100 grams of something, okay? After a half-life of 15 seconds, you're gonna have 50 grams left. You're gonna have half of it. After the next 15 seconds, you're gonna have half of 50, which is 25. After the next 15 seconds, you'll have half of 25, which is 12 and a half. After the next 15 seconds, you'll have half of 12 and a half, which is 6.25. You get the idea, okay? The half-life is the time it takes for half to go away. So the half-life is the 15 seconds, all right? That's for one chemical. For another chemical, the half-life might be a year. So you start with 100 grams, a year later you have 50. A year later you have 25. A year later you have 12 and a half. This time, 1 year is the half-life. Different chemicals have different half-lives. All right, let's say you've got another chemical. This one has a half-life of 1 billion years. Okay, so after 1 billion years, your 100 grams has gone down to 50. After another 1 billion years, your 50 has gone to 25. You get the idea. So that's what half-life means. It's the time required for half of your sample to be left. The key to doing half-life problems is to start with 0 half-lives, 0 time, and all of your sample. You want to start before the reaction begins. That's why you have 0 half-lives and 0 time. It hasn't started yet. And you have all of your sample because none of it has decomposed yet. Let's look at this example. If the half-life of a radioisotope is 20 years, how long will it take for a 40-gram sample to decay to 2.5 grams? Start with 0 half-lives, 0 time, and all of your sample. We are starting with 40 grams and we're decaying down to 2.5. So 40 grams is everything. Now we want to take 40 and half it until we get down to 2.5. So half of 40 is 20, half of 20 is 10, half of 10 is 5, and half of 5 is 2.5. And there we are. We're now down to 2.5 grams. Now count how many half-lives that took. Start with 0. After 1 half-life we had 20. After 2 we had 10. After 3 we had 5. After 4 we had 2.5. Now, it tells us the half-life, 1 half-life, is 20 years. So 1 half-life and 20 years go together. 2 half-lives would be 2 times 20, which is 40 years. 3 half-lives would be 20 times 3, which is 60 years. And 4 half-lives, 20 times 4, is 80. Notice we're not doubling this. You only have the amount left. This, you go up by 20 years each time if 1 half-life is 20 years. So the final question asked, how long will it take to get down to 2.5 grams? 2.5 grams to get there took 80 years. So 80 years is our answer. Let's look at another example. What is the half-life of a substance if a quarter of a sample remains after 24 minutes? Start with 0 half-lives, 0 time, and all of your sample. Wait a minute, they forgot to tell us how much we had. That's okay. They told us that we have 1/4 of it left. So we must have started with 1 whole sample to begin with. After a half-life, you'll have half of it left, and after another half-life, you'll have half of a half, which is 1/4. Just double the bottom number each time. So the next half-life would be 1/8, 1/16. You get the idea. Now, how many half-lives did it take to get there? 0, 1, 2. They also want to know what is the half-life. They want to know what is 1 half-life. They want this number here. They told us that you have 1/4 of a sample after 24 minutes. 1/4 and 24 minutes go together. So write your 24 minutes beside 1/4. Then 24 minutes divided by 2 gives us 12 minutes, which is 1 half-life. That is our answer. Next, there are 2 categories of types of nuclear reactions. There's fission and there's fusion. When an atom splits apart, that's fission. When two atoms are fused together, that's fusion. All right, so the way I remember the difference, fizz is the sound bubbles make when they pop. So fission is popping apart. Fusion is fusing it together, sticking it together. So there you go. So fission occurs when one large atom is hit by a neutron and splits into two smaller ones. You get a really high energy, fast moving neutron, and it slams into this large atom, which is a radioisotope. It's a radioactive isotope that would like to break into smaller, more stable isotopes of different atoms. So this neutron adds just enough instability to the atom that it breaks apart. It makes two smaller atoms, plus it gives off two more neutrons. Each of those neutrons is moving fast. Each of those hits a large atom, another of the same type of large atom, and splits it into two more small atoms each and two more neutrons each. So now we have 4 neutrons. They go and hit 4 atoms. They react. They give off 8 neutrons. Then they 16, 32, 64, 128. It just doubles and doubles and doubles and doubles and goes crazy. That is a chain reaction. And that's what causes a nuclear bomb, is that chain reaction. It starts out slow. 1 makes 2, makes 4, makes 8, makes 16. Whoop-de-doo. That's barely increasing. But if you'll try it on a calculator. All right, that was 3, 4, 5, 12, 13. Wow. After 13 times, we're up to 8,000. 14, 19. After 20 times of doubling, we're up to 1,000,000. That's crazy, isn't it? So this is why this explodes. Because at first it's reacting really slowly, but then it keeps doubling and doubling and doubling, and it just crazy explodes and gets really big. This is the same way that coronavirus spreads. If it doubles every week, at first, it's no big deal. Oh, whoop-de-doo, 16 people have coronavirus. We're not worried. If it doubles for 20 weeks in a row, that's not good. That's crazy. At first, it doesn't seem like anything's happening. And then all of a sudden it goes crazy and increases like crazy, and that's called exponential growth. This is also the same way that bacteria grow. At first, one bacteria splits up into 2. And then 2 bacteria split up into 4. It's no big deal. Whoopie-doo, we have 4 bacteria. Okay, a few more times. Okay, we have 16, 32, 64. Who cares? All of a sudden, you got 1,000,000 bacteria. And then when the 1,000,000 bacteria doubles, all right, it goes kind of crazy. So this is why exponential growth can just come out of nowhere and all of a sudden be increasing like crazy. So this is how nuclear fission happens. It fissions exponentially. And that's how a nuclear bomb happens, because all of a sudden it's increasing so fast and getting so hot, everything just explodes. This is also why in a nuclear power plant, you have to be very careful to keep the nuclear fission under control. What you do is you add cadmium control rods. There's a big old nuclear reactor, and inside that nuclear reactor there are cadmium control rods. Cadmium is a metal that can sop up some extra neutrons without undergoing fission and just reacting like crazy. It can take the extra neutrons and nothing happens. So you put the cadmium control rods down into the nuclear fission reaction and it slows it down. And then, let's say it's later in the day, everybody's coming home from work, they're taking a shower, they're turning on the lights, they're cooking supper, they're washing clothes, so they're using a lot more electricity. So then they pull the cadmium control rods out in the nuclear power plant, and the reaction goes faster and makes more electricity. Then everybody goes to bed at night, they put the cadmium control rods back in the reaction, slow it down, because not as many people need as much electricity at night. And that's how that works. All right, fusion is the opposite of fission. You take 2 small atoms and combine them to a bigger atom. For example, on the sun, 2 or 4 hydrogen atoms will combine and make one helium atom. And then multiple heliums can combine and make yet another atom. But on the sun, it's hydrogens making helium. So let's talk about the difference between fission and fusion. First of all, fission is like bubbles popping or fizzing. They pop apart. Fusion is combining or fusing together. Nuclear fission occurs in power plants and bombs. Nuclear fusion occurs on the sun. Nuclear fission produces nuclear radiation. Fortunately, nuclear fusion does not produce any radiation. You just have helium. Okay, so you talk like Mickey Mouse, that's about it. That's actually a very safe reaction. We wish we could use fusion in our power plants. It gives off more energy. Notice more energy. It does not make radioactive products. This would be our ideal reaction to produce energy and electricity. The problem is we can't catch the energy yet. It gives off so much energy all over the place. We are not good at catching that energy, so it's not very useful to us yet. There are some companies getting close to being able to use nuclear fusion, which would solve a whole bunch of our energy problems and all that, make us not so dependent on gasoline. We would be for a while, but eventually we would be much less dependent on that. And that would be a great advance for our world and for the health of our world and the environment and all that. So we hope one day we can use nuclear fusion reactors instead of nuclear fission reactors.